everyone, and welcome. Today, we're diving deep into data science.
Oh, yeah.
We've got some excerpts here from Introduction to Data Science, a Python approach.
Great book.
Really going to break down what data science is all about and how we can actually use it.
Awesome.
So before we get into the nitty-gritty, just what is data science?
Right.
I mean, is it just a fancy new name for statistics, or is there more to it?
It's definitely more than just statistics.
Okay.
It's really a way to think about
Yeah.
how we take data
Mhm.
and turn it into decisions.
Okay.
So it's not just about crunching numbers.
Right.
It's about understanding the world better,
Yeah.
making predictions, and then, choosing smarter actions based on those
So
predictions.
there's that practical side to it.
Yeah.
Now, the book mentions that data science is different from older approaches like business intelligence.
Yeah.
How so?
Well, business intelligence is often about looking backwards.
Okay.
It's about reporting on what's already happened.
Mm.
Data science is more forward-looking. It's about using that information from the past to guide us into the future.
I see.
So whether it's predicting what customers will buy or understanding complex things like the stock market, data science is about using data to make better decisions.
Okay, so it's more about using the data we have to kind of plan ahead.
Exactly.
Right. Now, the book talks about 4 main ways
Yeah.
that data science helps us explore the world.
Mm-hmm.
The first one is probing reality,
Right.
which sounds kind of sci-fi to me.
It's actually pretty straightforward.
Okay.
It's about using experiments to gather data and see what actually works.
So is that kind of like A/B testing, but on a grander scale?
Exactly.
Okay.
You're testing different versions of something,
Mhm.
like a website, to see which one performs better.
Right.
And that's how you get insights into what actually works.
Okay, so we're probing, we're experimenting, we're seeing what happens.
Yeah, exactly.
Now, the next one is pattern discovery.
Right.
What is that all about?
So think about how companies personalize your ads.
Yeah.
They're using data science to find patterns in your online behavior and the behavior of people like you.
Okay.
And that's how they figure out what you might be interested in.
Right, so it's kind of like
Mhm.
grouping people based on their behavior and then saying, okay, well, this group of people likes this, so we'll target them with that.
Yeah.
Exactly. That makes sense.
Yeah.
And then we've got predicting future events, which I think is what a lot of people think of when
Yeah.
they hear data science.
Definitely. That's a big part of it.
So what does that involve?
Well, it's all about using data to forecast what might happen in the future.
Okay.
And, this lets us be more proactive and make better decisions instead of just reacting to things as they happen.
Okay, so instead of just putting out fires, we can prevent them from starting in the first place.
Exactly.
Okay, I like that. And then the final one, revealing truths.
Right.
Sounds pretty deep.
It's about using data to illuminate things we might not otherwise see. So, for instance, scientists can use data to track disease outbreaks
Oh, wow.
and understand how to prevent them from spreading,
Okay.
or economists can use data to study how different policies impact the economy.
Interesting.
It's really about using data to uncover those hidden truths and make more informed decisions.
Right. So it's almost like data science can be a tool to help us
Hmm.
see things more clearly
Absolutely.
and make better decisions based on what we learn.
Yeah,
So data science can help us understand the past, navigate the present, and prepare for the future.
exactly.
Pretty powerful stuff. But how do we actually do data science?
Yeah.
The authors really emphasize using Python. Why is that?
Well, Python is a great language for data science, even if you're a beginner.
Okay.
It's relatively easy to learn. It's got a ton of libraries specifically for handling data, and there's a huge community of people who can help you out.
So it's beginner friendly, but also powerful enough for serious data science work.
Yeah, that's the beauty of Python.
Now, the book mentions some key Python libraries: NumPy, SciPy, Pandas, and scikit-learn. It sounds like those are kind of the essential tools in a data scientist's toolkit.
They're definitely your go-to libraries for data science in Python.
Can you give us a quick rundown of what each one does?
Sure. So NumPy is like the foundation.
Okay.
It handles all the heavy mathematical lifting, especially when working with arrays.
So it's kind of the brawn.
Yeah, you could say that.
Where does SciPy fit in?
SciPy builds on NumPy
Okay.
and provides even more advanced tools for things like optimization, statistics, and signal processing.
So it's like NumPy on steroids.
Yeah, kinda.
All right. And then we've got Pandas. What's its role?
Pandas is all about data manipulation and analysis.
Okay.
It helps you clean, transform, and explore your data in an efficient way.
So it's like a supercharged spreadsheet.
You got it. It's especially handy for working with tabular data, which is super common in data science.
And finally, scikit-learn. Is this where the machine learning magic happens?
Exactly. Scikit-learn is your one-stop shop for machine learning algorithms.
Okay.
Whether you're doing classification, regression, clustering, or anything else, Scikit-learn has got you covered.
It's like the machine learning Swiss Army knife.
You could say that.
Okay, so we've got our Python toolkit ready to go. But before we start building those fancy machine learning models, we need to actually understand the data itself.
Right.
The book dives into descriptive statistics. Why is that so important for data science?
Descriptive statistics helps us summarize and simplify our data.
Okay.
So it's about calculating things like the average, the spread of the data, and looking for any interesting patterns.
So it's about getting a feel for the data before we do anything fancy with it.
Exactly.
Yeah.
It helps us understand what we're working with before we dive into more complex analysis.
Now, the book really emphasizes the importance of data preparation.
Mm-hmm.
Why is that step so crucial?
Well, the thing about like cooking, you wouldn't just toss a whole onion into a soup, right?
Right.
You'd chop it, maybe dice it, depending on the recipe. Data preparation is kind of like that.
Okay.
It's about cleaning and formatting your data so it's ready to be analyzed.
So getting rid of the bad stuff, making sure everything's in the right format.
Yeah, exactly.
Okay, that makes sense. The book then jumps into some key statistical concepts. We've got population and sample. Can you remind us what those are all about?
Sure. So the population is the entire group you're interested in.
Okay.
But studying everyone is usually impossible, so we take a sample,
Right.
which is a smaller group that represents the population.
Like if you wanted to understand the opinions of everyone in a city, you'd survey a few hundred people, not the entire population.
Exactly. And we use that sample to draw conclusions about the larger population.
Okay, that makes sense. Now, two common ways to describe data are the mean and the median.
Mm-hmm.
The mean is the average,
Right.
and the median is the middle value when the data is ordered. Now, the book gives an example of analyzing age differences between men and women with high incomes. Can you explain how that illustrates the difference between the mean and the median?
Sure. So imagine you have a group of high earners, and there are a few men who are much older than everyone else.
Okay.
Those outliers would pull up the average age for men, making it seem like men are typically older.
Right.
But the median age wouldn't be affected as much by those outliers, giving a more representative view.
So in that case, the median would be a better measure of the typical age.
Exactly.
Okay, that's a great example of why choosing the right measure is important.
Absolutely.
The book also mentions standard deviation. What does that tell us about our data?
Standard deviation measures how spread out the data is around the average.
Okay.
So a small standard deviation means the data points are clustered close to the mean, while a large standard deviation indicates more variability.
Okay, I'm trying to think of a good analogy. So it's like, if you're measuring the consistency of a basketball player's free throws, a consistent player would have a low standard deviation.
Exactly.
While an inconsistent player would have a higher standard deviation.
Yeah, that's a great way to think about it.
Okay, so standard deviation tells us how much the data points vary.
Mm-hmm.
Now, what about outliers? Those data points that seem really out of place.
Outliers can be data entry errors, or they can be genuine but extreme values.
Okay.
And they can sometimes skew our analysis.
So we need to be careful about those.
Yeah.
The book talks about data visualization, which is using graphs and charts to make sense of the data.
Right.
Why is that so important?
Visualizations help us see patterns and trends that might be hidden in rows and rows of numbers.
Right, because sometimes it's hard to make sense of just a big table of numbers.
Exactly.
It's easier to see the story when you put it into a visual format.
Absolutely.
The book mentions histograms and cumulative distribution functions, or CDFs, for analyzing the age distribution of working men and women. What could we learn from those visualizations?
So histograms show us the distribution of the data,
Okay.
like how many people fall into different age brackets.
Yeah.
And CDFs show us how those numbers accumulate.
Okay.
So like what percentage of the workforce is under 30, under 40, and so on.
Got it.
And this can reveal interesting differences between groups, like men and women.
So we can see if there are any patterns or trends
Right.
based on those visualizations.
Exactly.
The book also talks about kernel density estimation. What's that all about?
Kernel density estimation is a way to smooth out a histogram
Okay.
and create a continuous curve that represents the distribution of the data.
So is it kind of like taking a blurry photo and sharpening it to see more detail?
That's a great analogy.
Okay, so we've explored ways to summarize and visualize our data.
Yeah.
Now, the book moves on to statistical inference. What is that, and why is it important?
While descriptive statistics is about describing the data we have, Statistical inference is about making broader statements about the population we don't have complete data on.
Yeah.
So it's about using a sample to draw conclusions about a larger group.
So it's like taking a small piece of the puzzle and trying to figure out what the whole picture looks like?
Yeah, exactly.
The book mentions two approaches to statistical inference.
Yeah.
Frequentist and Bayesian.
Right.
What's the difference between those two?
Frequentist statistics is based on the idea of repeated experiments.
Okay.
So it's about looking at how often something happens over many trials.
Like flipping a coin a bunch of times and seeing how often you get heads?
Exactly. Bayesian statistics, on the other hand, incorporates prior knowledge into the analysis.
Okay.
So it's about using what we already know to update our beliefs based on new data.
So Bayesian statistics takes context into account.
Yeah, you could say that.
The book also discusses the concept of variability in estimates. What does that mean and why should we care?
Well, any estimate we make from a sample is just that, an estimate.
Right.
And it's likely to be off from the true value for the entire population.
Because we're only looking at a small piece of the puzzle.
Exactly.
So variability in estimates acknowledges that there's going to be some uncertainty.
Yeah.
The book mentions that traditional methods use theoretical approximations, but now we have these fancy simulation-based techniques,
Right.
like bootstrapping. What's so cool about that?
Bootstrapping lets us estimate the variability of our estimates without relying on complex mathematical formulas.
Okay.
We essentially create multiple fake data sets by resampling from our original data
Okay.
and then see how much our estimates vary across those fake data sets.
It's like running a bunch of simulations to see how much our results might change.
Yeah, exactly.
So we're getting a sense of how robust our estimates are.
Right.
The book then dives into confidence intervals. Can you explain what those are and why they're useful?
A confidence interval gives us a range of plausible values for a population parameter,
Okay.
along with a level of confidence.
Okay.
So, for example, we might say, we're 95% confident that the true average height of people in this city falls between 5'8" and 5'10".
So it's like saying, we're pretty sure the true value falls within this range, but we can't be 100% certain.
Exactly.
The book uses the example of analyzing daily traffic accidents in Barcelona to illustrate confidence intervals. Why is this a relevant example?
Imagine you want to know the average number of accidents per day in Barcelona, but you only have data for a few months.
Okay.
A confidence interval would give you a range of values that likely contains the true average, acknowledging that your limited data might not give you the exact answer.
So it's like acknowledging that there's some wiggle room in our estimate.
Exactly.
The book then moves on to hypothesis testing. What's that all about, and how does it relate to confidence intervals?
Hypothesis testing is about testing specific claims about a population.
Okay.
We start with a null hypothesis, which is like our default assumption,
Okay.
and then we look for evidence to either support or reject that assumption.
So it's kind of like a scientific experiment.
Yeah, you could say.
We have a hypothesis, and we're trying to see if the data supports it.
Exactly.
The example given is comparing traffic accidents in Barcelona between 2010 and 2013. How would you set up a hypothesis test in this case?
Our null hypothesis might be that there's no difference in the average number of accidents between those 2 years.
Okay.
And then we'd collect data and see if there's enough evidence to reject that null hypothesis.
So we're looking for data that's strong enough to say, hey, something interesting is going on here. It's not just random chance.
Exactly.
The book mentions p-values, which are often misinterpreted.
Yeah, p-values can be tricky.
Can you shed some light on what they actually mean?
A p-value is the probability of getting the results we observed if the null hypothesis were true.
So a small p-value suggests that our data is unlikely under the null hypothesis, which makes us suspicious.
Yeah, it makes us think that maybe something else is going on.
But the book warns against confusing statistical significance with practical importance.
Absolutely.
Why is that distinction so crucial?
Well, just because something is statistically significant doesn't mean it's actually meaningful in the real world.
Right, like finding a tiny difference between two groups that doesn't really matter in practice.
Exactly. We need to consider both statistical and practical significance when interpreting our results.
So we need to be careful about getting too excited about a statistically significant result if it doesn't have any real-world implications.
Yeah, that's a good point.
Now, the book jumps into a whole new area, supervised learning. This is where machine learning really starts to take center stage, right?
Absolutely. Supervised learning is all about teaching machines to learn from labeled examples.
Okay.
So you have a data set where each example is labeled with a specific outcome, and the algorithm learns to predict that outcome for new examples it hasn't seen before.
Like training a spam filter.
Exactly. You give the algorithm a bunch of emails labeled as spam or not spam, and it learns to identify the patterns that distinguish them.
Right.
So it can then classify new emails as spam or not spam based on what it's learned.
Okay, that makes sense.
Yeah.
Now, the book differentiates between classification and regression. Can you illustrate the difference with some real-world examples?
Sure. Predicting whether a loan application will be approved or denied is a classification problem.
Okay.
Because you're trying to put it into one of two categories, approved or denied.
So categories, got it.
But estimating the market value of a house is a regression problem.
Okay.
Because you're trying to predict a continuous value, which is the price of the house.
So classification is categories, and regression is more like a continuous scale.
Exactly.
The book mentions performance evaluation, model selection, and overfitting. Why are those concepts so important in supervised learning?
Well, performance evaluation is about measuring how well our model is doing.
Okay.
Model selection is about choosing the right model for the job.
So picking the right tool for the task at hand.
Exactly. And overfitting is a trap where our model might perform really well on the data it was trained on, but then fail miserably on new data.
So we need to make sure our model can generalize to new data.
Yeah.
Not just memorize the data it's already seen. The book then introduces two specific learning models.
Yeah.
Support vector machines, SVM, and random forest, RF.
Mm-hmm.
Let's start with SVM. What's the basic idea behind that model?
Imagine you're trying to draw a line to separate two groups of points on a graph.
Okay.
SVM is about finding the best line, or hyperplane in higher dimensions. That separates those data points belonging to different classes.
So it's like finding the best boundary to divide the data.
Yeah, you got it.
And the maximum margin hyperplane, what does that mean visually?
It's like finding the widest possible street that separates those two groups, ensuring each group stays on its own side of the street.
So we're maximizing the separation between the group.
Exactly.
Okay, that makes sense.
Mm-hmm.
Now, the book mentions kernels.
Mm-hmm.
Those can get pretty technical.
Yeah, they can be a bit tricky.
Can you give us a simplified explanation of why they're used in SVM?
Sometimes the data points can't be separated neatly with a straight line. Kernels let us transform the data into a higher dimensional space where we can then find a separating hyperplane.
So it's like taking a tangled mess of yarn and stretching it out so you can see how to separate the different colors.
That's a great analogy.
Okay, so kernels help us untangle the data to make it easier to classify.
Exactly.
Now let's move on to random forest.
Okay.
What's the core concept behind that model?
Random forest is all about combining the predictions of multiple decision trees.
Okay.
Each tree gets a vote, and the majority rules.
So it's like a democratic decision-making process for our data.
Yeah, exactly.
Why is random forest particularly good at avoiding overfitting?
Because it combines the predictions of multiple trees.
Mm-hmm.
It's less likely to be swayed by any single tree memorizing the training data too well.
So it's like getting advice from multiple experts instead of just relying on one.
Yeah, you get a more balanced perspective.
The book then dives into a case study using SVM for a marketing campaign.
Mm-hmm.
Why is this a particularly insightful example?
It highlights that just having the most accurate predictions isn't always the goal.
Okay.
Sometimes you need to consider the costs and benefits associated with different types of errors.
Right.
So, for example, in a marketing campaign, it might be more costly to miss a potential customer than to target someone who's not interested.
So we need to align our data science approach with the specific goals of the task.
Exactly.
Okay, now let's shift gears to unsupervised learning, specifically clustering. What's the key idea behind clustering?
Clustering is about grouping data points based on their similarity without having pre-labeled examples to learn from.
So it's like sorting a basket of laundry without knowing which clothes belong to whom.
That's a good analogy.
You're just trying to group things together that seem similar.
Yeah, exactly.
The book mentions various metrics for evaluating clustering performance.
Mm-hmm.
This seems tricky since we don't have those correct labels to compare against.
It is. Metrics like the RAND index and silhouette coefficient try to capture how well our clusters reflect the underlying structure of the data, even without knowing the true groupings.
So we're looking for metrics that tell us how meaningful our clusters are, even if we don't have a ground truth to compare them to.
Exactly.
The book introduces several types of clustering algorithms, partitional, hierarchical, and density-based. Can you briefly explain each type and give some examples of where they might excel?
Sure. So partitional algorithms, like k-means, try to divide the data into distinct, non-overlapping clusters.
Okay.
Hierarchical clustering builds a tree-like structure of clusters.
So it's like creating those nested categories?
Yeah, like a family tree.
And density-based clustering.
Density-based algorithms look for areas where data points are densely packed together.
So it's like identifying clusters of stars in the night sky.
Exactly.
We've got different clustering algorithms for different types of data structures.
Yeah, each algorithm has its strengths and weaknesses.
Now, the book shifts gears to network analysis. Why is network analysis such a powerful tool?
Network analysis helps us understand relationships and connections, which are everywhere.
Yeah, I mean, social networks are an obvious example, but it goes beyond that, right?
Absolutely. We can use network analysis to study transportation systems, the spread of information online, even the interactions between molecules in a cell.
It's like we're mapping out the connections that make up our world.
Exactly.
The book introduces some key network concepts: nodes, edges, directed and undirected graphs.
Mm-hmm.
Can you give us a quick tour of these concepts using a familiar example like Facebook?
Sure. So on Facebook, each person is a node.
Okay.
And the friendships between them are the edges.
So nodes are the entities and edges are the relationships.
Exactly.
What about directed and undirected graphs?
Well, on Facebook, friendship is mutual.
Right.
So the edges are undirected.
Okay.
But on Twitter, you can follow someone without them following you back.
Mm-hmm.
So the following relationship is directed.
Okay, so the direction of the arrow indicates who's following whom.
Right. What about degree centrality? What's that all about?
Degree centrality measures how connected a node is.
So on Facebook, someone with high degree centrality would have a ton of friends.
Exactly. And
Yeah.
they'd be considered more influential in the network.
So it's about popularity in a way.
You could say that.
The book also mentions paths and shortest paths. What are those?
A path is a sequence of nodes connected by edges,
Okay.
like tracing a route from your profile to a friend's profile by hopping through mutual connections.
And the shortest path is the most efficient way to get from one node to another.
Exactly.
What about connected components?
Connected components are groups of nodes that are all connected to each other.
So like a group of friends who all know each other.
Right.
What about weighted graphs?
Weighted graphs assign weights to the edges,
Okay.
which can represent things like the strength of a connection or the distance between two nodes.
So we're adding more information to the network.
Yeah, we're capturing the intensity or importance of the connections. The book then delves into centrality measures. What are those all about?
Centrality measures help us identify the most important nodes in a network.
Okay.
But importance can have different meanings.
So there are different ways to measure importance in a network.
Exactly. We already talked about degree centrality, but there are others like between-ness centrality and closeness centrality.
Can you give some real-world examples to illustrate those other centrality measures?
Sure. Between-ness centrality measures how often a node lies on the shortest path between other nodes.
Okay.
So a person with high between-ness centrality might be someone who connects different groups of people who wouldn't otherwise know each other.
So they're like the social connectors.
Yeah, the bridges between different communities.
What about closeness centrality?
Closeness centrality measures how easily a node can reach all other nodes in the network.
So it's about being in a strategic location, easy to get to from anywhere else.
Exactly.
Like a major transportation hub.
Yeah, that's a good analogy.
What about eigenvector centrality? That one sounds a bit more complex.
Eigenvector centrality takes into account the influence of a node's neighbors.
Okay.
So it's not just about how many connections you have, but also about the quality of those connections.
So if you're connected to a bunch of influential people, you're more likely to be influential yourself.
Exactly. It's like the saying, the company you keep.
The book then introduces community detection. What's that about?
Community detection is about finding groups of nodes that are more densely connected to each other than to nodes in other groups.
So like identifying the different cliques in a high school.
Right, or the different neighborhoods in a city.
The book mentions ego networks. What are those?
An ego network is a network centered around a specific individual,
Okay.
including their direct connections and the connections between those connections.
So it's like mapping out your own personal social circle.
Yeah, exactly. And by analyzing ego networks, we can get insights into how communities form.
So we're zooming in on individuals to see how they contribute to the larger network structure.
Exactly.
The book then jumps to recommender systems. Those are pretty familiar to most of us from websites like Amazon and Netflix.
Yeah, they're everywhere these days.
What's the basic idea behind them?
Recommender systems try to predict what you might like based on your past behavior or the preferences of people similar to you.
So it's all about suggestions, helping us discover things we might enjoy.
Exactly.
The book mentions content-based filtering and collaborative filtering. Can you explain those two approaches?
Sure. Content-based filtering recommends items that are similar to things you've liked before.
Okay.
So if you listen to a lot of jazz on Spotify, content-based filtering might recommend other jazz artists or songs with similar musical characteristics.
So it's finding similar items.
Right.
What about collaborative filtering?
Collaborative filtering finds people with similar tastes to you
Okay.
and recommends things they like.
So it's finding similar users. The book gives Pandora as an example of a content-based filtering system. What makes Pandora a good example?
Pandora analyzes songs based on hundreds of musical attributes, creating a music genome for each song.
Interesting.
And they can then recommend songs with similar genomes,
Okay.
even if they're by different artists or from different genres.
So it's like finding musical soulmates.
Yeah, kind of.
The book then talks about evaluating recommender systems.
Right.
What are some of the challenges involved in measuring how well these systems are working?
Well, one challenge is that different people have different ideas of what a good recommendation is.
Right. Some people might want recommendations for things they already know they like,
Yeah.
while others might want to be surprised and discover new things.
Exactly.
Yeah.
It's hard to design a system that pleases everyone.
What are some metrics that can be used to assess recommender systems?
One common metric is RMSE,
Okay.
which stands for root mean squared error. It measures the difference between the system's predicted ratings for items and the user's actual ratings.
So it's measuring how accurate the predictions are.
Exactly.
The book then dives into a practical case study on building a movie recommendation system using collaborative filtering. What are some of the key steps involved? Welcome back. So, in part 1, we got through a whole bunch of data science fundamentals.
We did.
Now, I'm really interested to see how this stuff actually gets used in the real world.
Yeah, that's where it gets really exciting. You know, data science is being used to solve all sorts of problems.
Absolutely, and the book goes through a lot of them.
Yeah.
Let's start with sentiment analysis.
Okay.
This idea that we can look at text and figure out, like, the emotional tone behind it.
Exactly.
Like, can you really tell if a tweet is happy or angry just by looking at the words?
You can. Sentiment analysis is all about that, determining whether a piece of text is positive, negative, or neutral. It's super valuable for businesses, because they can use it to understand how people feel about their brand.
Yeah.
Or their products, or even their marketing campaigns.
So, like, a company could use sentiment analysis to see how people are reacting to their new ad campaign.
Exactly. They could look at social media posts, reviews, even survey responses.
And then they could kind of adjust their strategy based on what they learn.
Exactly. It's like having a finger on the pulse of what people are thinking and feeling.
That's really cool. The book gets into some of the technical details
Yeah.
about how sentiment analysis works, like data cleaning and text representation. It seems like getting the text data ready for analysis is a really important first step.
It is. It's like prepping your ingredients before you cook.
Right.
You got to clean and organize the text data before you can actually make sense of it.
Okay, so what are some of the techniques involved in that data preparation? The book mentions tokenization, stemming, and the bag of words model.
Right. So tokenization is like breaking down a sentence into individual words or tokens.
Okay.
So you have a sentence like, the quick brown fox jumps over the lazy dog. Tokenization would separate that into the quick brown and so on.
Okay, so it's kind of like separating all the ingredients in your recipe.
Yeah, you got it.
What about stemming?
Stemming is about reducing words to their root form.
Okay.
So running, runs, and ran would all become run.
So it's like using the core ingredient instead of all its different forms.
Right, it simplifies things.
And then what about the bag of words model? What's that all about?
So the bag of words model represents text as a collection of words, but it ignores the grammar and the order of the words.
Okay, so it's like throwing all the words from a sentence into a bag and just counting how many times each word appears.
Exactly. It's a simple but effective way to represent text for analysis.
Okay, so we've broken down the text, we've simplified it, and we've counted the words. What happens next?
Well, once we have our text represented in a way that algorithms can understand, we can start analyzing the sentiment. One way to do this is to use a lexicon, which is like a dictionary of words and their associated emotional tone.
Oh, so it's like we're looking up the emotional meaning of each word.
Yeah, exactly. Words like happy and love would have positive scores,
Okay.
and words like sad or angry would have negative scores.
So we're basically assigning a score to each word based on its emotional weight.
Right. And then you can analyze the overall sentiment of the text based on the scores of all the words.
The book also talks about n-grams, which I think takes things a step further.
Yeah, n-grams are sequences of words.
Okay.
So instead of looking at individual words in isolation, we're looking at pairs or triplets of words.
Right, because sometimes the meaning changes depending on the context.
Exactly. For instance, not good has a very different meaning from good by itself.
Right, so not good would have a negative sentiment,
Exactly.
while good on its own would have a positive sentiment.
Right.
The book walks through an example of using machine learning for sentiment analysis on movie reviews.
Yeah, that's a classic application of sentiment analysis.
So how does that work? Like, how do we teach a machine to understand whether a movie review is positive or negative?
Well, we can train machine learning algorithms like naive Bayes or support vector machines on a data set of movie reviews that have already been labeled as positive or negative.
Okay.
And by analyzing those labeled examples, the algorithm learns to identify patterns in the language that are associated with positive or negative sentiment.
So it's like showing the algorithm a bunch of examples and letting it figure out the rules for itself.
Exactly. And once it's learned those rules, it can then predict the sentiment of new unseen movie reviews.
So it's kind of like teaching a kid to ride a bike.
Yeah.
You show them how to do it a few times and then they eventually figure it out on their own.
Exactly. And the more data we have, the better the algorithm will be at predicting sentiment.
The book also emphasizes the importance of testing these models.
Absolutely. You got to make sure they're actually working.
Right. So we need to make sure that the algorithm is actually able to predict the sentiment of new reviews accurately.
Exactly. We can't just assume that it will work perfectly. We need to test it and see how it performs.
Okay, that makes sense. Let's shift gears back to one of the concepts we talked about in part 1, clustering.
Okay.
Remember, clustering is about grouping data points based on their similarity. You mentioned there are different types of clustering algorithms, each with their own strengths and weaknesses. What are some of the key factors to consider when choosing a clustering algorithm?
Well, one important factor is the shape of your clusters.
Okay.
Some algorithms, like k-means, are really good at finding those nice, compact, spherical clusters. But if your clusters are more irregularly shaped, like swirls or curves, then k-means might not be the best choice.
Right, because it's like trying to fit square pegs into round holes.
Exactly. In those cases, you might want to use an algorithm like spectral clustering or density-based clustering.
So we're choosing the right tool for the job based on the shape of our data. What else should we consider?
Another important factor is the size of your data set.
Okay.
Some algorithms can get really slow when you have a lot of data.
Right. It's like trying to sort a million Legos by hand.
Exactly. So for those really big data sets, you need algorithms that are more scalable and efficient.
So what are some examples of those more efficient algorithms?
K-means and DBSCAN are both pretty good at handling large data sets.
So if you've got a mountain of data, those are the algorithms you want to reach for.
Right.
The book also mentions that the number of clusters you're looking for can influence your choice of algorithm.
Absolutely. Some algorithms, like k-means, require you to specify the number of clusters beforehand.
Okay, so you have to tell it, I want you to find 5 clusters in this data.
Exactly. But other algorithms, like hierarchical clustering, don't require you to specify the number of clusters up front.
So you get more flexibility with hierarchical clustering.
Right. It gives you a hierarchy of clusters, and you can decide where to cut the tree to get the number of clusters you want.
It's like having a branching tree of categories, and you can decide how many branches to keep.
That's a good way to put it.
The book highlights a case study using clustering on data from the Eurostat database. Can you tell us about that?
This case study shows how clustering can be used to group countries based on their economic and social indicators.
Oh, wow.
Like GDP, unemployment rate, and life expectancy.
So we can see which countries are similar to each other based on those factors.
Exactly. And that can help us understand patterns in economic development and identify potential areas for collaboration.
So we're creating those country groupings based on data.
Yeah, it's a powerful way to make sense of complex data and identify meaningful patterns.
Let's switch back to network analysis.
Okay.
We talked about how it can be used to understand relationships and patterns of influence.
Right, it's all about connections.
The book has an example of using network analysis to understand relationships and influence within a social network.
Yeah, social networks are a great example of where network analysis can be really insightful.
So imagine we're analyzing a network like Twitter. What kind of things could we learn from that?
Well, by mapping out the connections between users who follows, whom we can identify influential individuals.
Right, so those would be the people with lots of followers and lots of retweets.
Yeah, but we can also look beyond just the number of followers.
Okay.
We can use centrality measures to identify people who play key roles in the network.
So we can see who's really driving the conversation.
Exactly. For example, people with high betweenness centrality often act as bridges between different communities.
Oh, so they're like the social connectors?
Yeah, they connect different groups who might not otherwise interact with each other.
That's interesting.
Yeah, and they can be very influential in spreading information and ideas.
The book also mentions community detection within networks. What's that all about?
Community detection is about finding groups of nodes that are more densely connected to each other than to nodes in other groups.
Okay.
So it's like identifying the different clusters or communities within a larger network.
So in the Twitter example, we might find communities of people who are interested in specific topics.
Exactly. Like sports fans, music lovers, or political activists.
The book talks about a Facebook network that was manually labeled into ego networks. Can you remind us what those are?
Sure, an ego network is a network centered around a specific individual.
Okay.
It includes their direct connections and the connections between those connections.
So it's like mapping out your own personal social circle.
Exactly. And by analyzing ego networks, we can see how communities form around individuals and how those communities interact with each other.
Okay, so we're zooming in on those individual social circles.
Yeah.
To see how they contribute to the larger social fabric.
Right.
Now, recommender systems are all about understanding human behavior and predicting our preferences.
They are, and they're getting more and more sophisticated all the time.
The book digs into the details of building a movie recommendation system using collaborative filtering. It's pretty amazing how these systems can analyze all that data to figure out what movies we might like.
It is. Collaborative filtering is all about harnessing the collective wisdom of a user community to make personalized recommendations.
The book stresses how important it is to calculate user similarity for making those good recommendations.
Right. Finding those taste-alike users is key.
So how do we go about finding those users who share our taste in movies?
Well, we can use techniques like Euclidean distance and Pearson correlation to calculate how similar users are to each other.
We talked about those earlier.
We did. So Euclidean distance measures the straight line distance between two users in a multidimensional space.
Okay.
Where each dimension represents their rating for a movie.
So it's like finding your movie taste neighbors.
Yeah, exactly.
Yeah.
Users who are closer together in that space have more similar tastes.
What about Pearson correlation?
Pearson correlation measures how much two users' ratings tend to move together.
Okay.
So if one user loves a movie, a highly correlated user is also likely to love that movie.
Got it. So we can use these techniques to find users who have similar preferences and then use their ratings to make recommendations for us.
Exactly.
Let's get back to parallel computing. You mentioned earlier that it's becoming really important for dealing with those massive data sets and those complex analyses.
Absolutely. Parallel computing is like having a team of computers all working together to solve a problem.
And the book really highlights IPython's capabilities for parallel computing.
Yeah, IPython is great for that.
So how does IPython allow us to harness the power of multiple computers?
It provides a framework for coordinating those parallel computations.
Okay.
So you can think of it like having a team of workers or engines that can execute tasks. A manager or scheduler that assigns tasks to the workers.
Okay.
And a user interface or client that lets you interact with the whole system.
So it's like a well-organized construction crew. You've got the workers, the foreman, and the client who's overseeing the project.
Yeah.
You also mentioned there are different ways to assign tasks to the workers. Can you explain the difference between the direct view and the load-balanced view?
Sure. So the direct view lets you manually assign specific tasks to specific workers.
Okay.
This is useful if you have tasks that have very different computational demands, and you want to make sure they go to the right workers.
So it's like if you have a really heavy piece of furniture to move.
Yeah.
You want to make sure you assign that to the strongest movers.
Exactly. The load balance view, on the other hand, lets the manager automatically distribute tasks based on which workers are free.
So it's like the foreman just says, okay, you're free. Take this task.
Right.
The book uses the example of analyzing a huge data set of NYC taxi trips to illustrate the power of parallel computing.
Yeah, that's a classic big data problem.
Why is that such a good example?
Well, imagine trying to analyze millions of taxi trips on a single computer. It would take forever.
So parallel computing lets us speed things up by dividing the data into chunks and processing those chunks simultaneously on multiple computers.
Exactly. It's like having a team of analysts, each working on a different part of the data.
The book talks about the challenges of working with those really big data sets, things like data size and computation time.
Yeah, those are big challenges.
How does parallel computing help us overcome those challenges?
By distributing the data and the computation across multiple machines,
Okay.
we can break those massive tasks into smaller, more manageable pieces.
Right.
This reduces the overall processing time and lets us analyze data sets that wouldn't even fit on a single computer.
It's incredible how parallel computing opens up these new possibilities for analyzing really large and complex data sets.
Absolutely. It's a game changer for data science.
Okay, so we've covered a lot of fascinating concepts and applications in this part of our deep dive.
We have.
We've talked about sentiment analysis, clustering, network analysis, recommender systems, and parallel computing.
A lot of ground covered.
And it's really exciting to see how all of these tools and techniques are being used to solve real-world problems across so many different fields.
It is. And we're just scratching the surface of what's possible with data science.
Welcome back for our final deep dive into the world of data science. We've covered so much ground, from the basic concepts to really interesting real-world examples.
It's been quite a journey.
But I'm excited to see how these tools are actually being used to solve problems, to make a real impact.
Absolutely, and the book talks about just that.
Yeah.
How data science is changing the game in so many areas, from healthcare to finance, marketing, you name it.
And the book goes through several case studies.
Yeah.
I want to jump into the healthcare one.
Okay.
I'm always fascinated by how data science can improve diagnoses and treatment plans.
It's really revolutionizing healthcare.
Yeah.
One area where it's making a huge difference is medical image analysis.
Okay.
So using techniques like deep learning, algorithms can now analyze medical images, things like X-rays, CT scans, MRIs, to detect abnormalities. And they do it with incredible accuracy.
Wow, so these algorithms are like super-powered radiologists.
You could say that.
Able to spot things that a human doctor might miss.
Exactly. They can detect subtle patterns and anomalies that might not be obvious to the human eye.
So this could lead to earlier diagnoses, more accurate diagnoses.
Absolutely. And that's critical for effective treatment.
Absolutely.
Catching things early can make all the difference.
Now, the book mentions a case study where data science was used to predict patient readmission rates.
Yeah, that's a really important application.
So how does that work?
Well, you can analyze patient data, like their medical history, demographics, previous hospitalizations, and use that to identify patients who are at higher risk of ending up back in the hospital.
So it's like identifying those patients who need that extra care and support.
Exactly. And that can help prevent readmissions, which is better for the patients and the healthcare system.
It's a win-win.
Yeah.
I like that. Another area where data science is making a big splash is personalized medicine.
Oh, absolutely.
This idea that we can tailor treatments to individual patients, it sounds so futuristic.
It's becoming a reality. Personalized medicine is about using data.
Okay.
Things like a patient's genetic makeup, their lifestyle, environmental factors.
So we're moving away from that one-size-fits-all approach.
Exactly.
We can create customized treatments.
Yeah, treatments that are more effective and have fewer side effects.
The book talks about how data scientists can analyze huge amounts of data, like genetic information, medical records, lifestyle factors.
A lot of information.
And use that to predict how individual patients will respond to different treatments.
Right. It's all about finding those patterns in the data.
It's like having a personalized health map for each patient.
Yeah, you can think of it that way.
Amazing. Data science really is transforming healthcare.
It is.
And like you said earlier, we're really just at the beginning.
We are. There's so much more to come.
As we get better at collecting and analyzing data, the potential is just enormous.
Huge potential.
The book also highlights how data science is being used to address climate change.
Yeah, that's a really important application.
Which is one of the biggest challenges we're facing as a species.
Absolutely.
It's incredible to think that data can help us understand and tackle this global issue.
It can, and it is.
The book mentions using data science to optimize renewable energy sources like solar and wind power.
Right. So we can make the most of these clean energy sources.
So it's about figuring out the best places to put solar panels and wind turbines.
Exactly. Data science models can analyze weather patterns, energy demand, grid capacity, and all sorts of factors.
To make sure those renewable energy sources are being used efficiently.
Yeah, we want to maximize their impact.
And reduce our dependence on fossil fuels.
Absolutely. That's the goal.
The book also talks about developing smart grids that can adapt to those fluctuating energy demands and integrate renewable energy more seamlessly.
It's all about creating a more sustainable and resilient energy system.
I love that. Data science is helping us build a cleaner, more sustainable future.
It is, and it's exciting to see how it's being used to address such a critical issue.
Absolutely. Well, we've reached the end of our deep dive into data science.
We have.
And it's been an incredible journey.
Definitely lots to learn and explore.
We've gone from those fundamental concepts all the way to real-world applications. And it's clear that data science is a field with just unlimited potential.
Unlimited.
You know, from improving healthcare to tackling climate change, from personalizing our online experiences to helping us understand the world around us better. Data science really is changing everything.
It is, and it's only going to become more important as we move forward.
Absolutely. And as we generate more and more data, the role of data science is only going to become more crucial in helping us make sense of it all.
Exactly.
It's an exciting time to be alive in this data-driven world.
It is, and it'll be fascinating to see where data science takes us next.
Thanks for joining us on this incredible journey.